Just waiting the heads up from Noel. Okay. So good afternoon, everyone. Today we have Charles Greer. He is one of our own. He graduated with his BS and MS from University of Illinois, and he's a registered professional engineer from the states of Florida and Georgia. During his 41 plus years of experience, Greer worked on a broad range of global civil engineering projects. I'm a senior vice president, director of engineering, and director of quality assurance for law engineering, MACTEC, and MAC E&I. Here I was responsible for the development and implementation of engineering and quality procedures, as well as project management procedures. From 1974 to 2015, he was also involved in all the construction phases at the Hartsfield-Jackson Atlanta International Airport. Currently, he has taught the course case studies in infrastructure engineering for UIUC in our department since 2010, and he received the Teacher Excellent rating in the summer of 2016. Let's please welcome him.
Okay. Everybody here okay? Okay, good. I'd like to thank Hassan and Ahmad and the Center for letting me come chat with you today and share some experiences I've had over my career. We're going to talk about the world's busiest airport, and we'll explain what that means in a minute here. But I've had the opportunity to work in this project for over 40 years, off and on. I wasn't an employee of the airport, but I was consultant to the airport on just a whole host of projects there over the years. And so we look at Hartsfield. It's the busiest airport in the world, and until last year it had more than 107 million passengers pass through there. And I remember when we opened what's called Midfield in 1980, it was a big deal because that was going to handle 55 million passengers. And now we're at almost double that. Some things have been added, obviously, to allow that. But sometimes your estimates of capacity are too low on things. Beijing is fast coming up, though. It will probably overtake Hartsfield in the next 3 or 4 or 5 years. But right now, Hartsfield's the busiest in passengers. And until last year, it was also the busiest in operations. An operation being a landing or a takeoff. O'Hare passed it last year, and in the past years, O'Hare and Atlanta kind of go back and forth, who's the busiest. But Atlanta was a few thousand less, 895,000. But it's interesting to note, in 2007, Hartsfield was just shy of 1 million operations in a year. And then along came the Great Recession, as everybody calls it, and the number of operations has come down as airlines have shrunk operations. But if you've been on a plane lately, you know where they all went. Everybody's filled every seat. So, but anyway, just to give a flavor for busiest in passengers and has been busiest in operations a number of the last years. What's the history of Hartsfield? Well, in the beginning, it was pretty small. And it's kind of interesting. There was a article, in fact, I'll pull it out here, in the Atlanta newspaper just in the last week, 100 years ago, on March 31st, 1919. This article appeared in the paper, and I'll read it just quickly, it's fairly short. Atlanta will have aero landing place. Atlanta will soon have a suitable landing for every known make of flying machine through the efforts of former Mayor Asa G. Candler and the county commissioners at the old Automobile Speedway. So the airport used to be an old racetrack between Hateville and College Park. This has been assured after an investigation of the site by Colonel Townsend F. Dodd of the United States Air Service and members of the county commissioners who have given party approval of the plans. Visiting airplanes have used the site for landing purposes in the past, and with some improvements by the county, it is expected that the field will make an acceptable landing place for anything moving in the air that may visit Atlanta. And you kind of tell some of the literature of the 100 years ago how some of the language was. Mr. Candler agreed to donate the use of the site for the purpose, and it's expected that work on the field will be begun in the near future by the county. It has been proposed to name the site the Asa G. Candler Field in honor of the donor. Plans are now being considered by the county commissioners, indicate that the landing place will be complete within the next 30 days. Now that's pretty fast. So, but anyway, in the beginning, it was a fairly humble operation. In the 1960s and 70s, what came along was runway 8 right on the north side was rebuilt. This is the airport looking to the east. Runway 9 right was built in 1972. Runway 9 left was rebuilt in 1974. That was the first runway that I ever worked on in my career, and it's still out there, some 45 years later, serving as a takeoff runway, 200 to 250,000 departures a year. So it's pretty good for a 20-year design. And then in the 70s, late 70s, we built what's called midfield with the T concourse that's first, and then the 4 A, B, C, D concourses. And you see pretty nice improvement to the airport. In the 80s, we built the 4th runway on the north side. So now Hartsfield had 2 runways on the north and 2 runways on the south. Great improvement for operational capacity. Concourse E was a new international terminal built towards the east of midfield. That was done in the early 90s. And in 2005, the 5th runway, far to the south side, was completed. So by 2005, the airport now had 5 runways and capacity to shut down any one of these and utilize the runway down there, because you have, I think it's, I can't remember the exact number, but it's like 4,200 feet or maybe a mile between runways to have simultaneous operations side by side. As we move ahead, in 2011, the Maynard-Jackson International Terminal was built. It added 9 gates to the airport, and it cost a mere $1.2 billion, a little bit more than they planned on. Midfield, which was built in the 70s, cost $400 million, and that included the terminals, the pavements, everything. So a little bit different. Now if you go down to Hartsfield and you drive in, you'll see these nice big sweeping canopies that are being constructed to give it an even more modern look to this 40-year-old airport. So that's a little bit of the history. And the canopies, the good thing about the canopies, which I think about $260 million, is they are now finally building elevated road pedestrian walkways. So after 40 years, you no longer have to dodge the cars. You'll be able to go up the escalator, cross, and get out of traffic. So it's come a long way from 100 years ago to where it is today. Now, you got to have efficient operations, because if you shut down a Hartsfield runway or taxiway, you mess up the whole country. It's like coming up here yesterday, coming through Nashville. Everything was going fine. Sarah looked at the map. Hey, everything's green. But by 10 o'clock when we got to Nashville, it took an hour to get through Nashville, all because one lane on 440 West had been shut down. And you have 24, 40, and 65 all coming together in the middle of town, shut even one lane down, you have major problems. So it took an extra hour. There's about 47 million square feet of concrete pavement at Hartsfield. That's 1,000 plus acres. You could pave 250 miles of 4-lane interstate, 12 inches thick, or the 2.4 million cubic yards, we could go out and build a 10,000-foot runway every year for 30 years. So it's a lot of concrete there. In fact, my father-in-law has a farm out at Farmer City, west of here, about 20 miles. I once told him, hey, you know, we could come out here, pave your entire farm, 400 plus acres, 3 feet thick, and we still have some concrete left over. So I think it's pretty, and the replacement value, who knows? We once estimated more than $1 billion. It's probably a couple of $1 billion to replace the concrete out there. So a lot of money, a lot of people count on it. Let's step back 10 years approximately to 2010. When we looked, Hartsfield's distribution of pavements was pretty level by decade. In other words, less than 10 years, about 25%. So 20 to 30% in each 10-year increment, and almost 25% was over 30 years. You know, 20-year designs, 30 years. I would caution you You know, when I got out of school, you talked about 20-year designs, and that was like forever. That was going to occur. But once you get out in practice, it comes like that. 20 years is going to go by in a heartbeat. So you need to be thinking in terms of 40 and 50-year pavements. And FAA, I think, is finally coming around to looking at that. But be thinking in long-term lives, because you just can't afford to shut things down every 20 years and redo them. Okay, they had a nice spread of things. Let's fast forward from 2010 to 2015. What happens? Well, if we don't build anything or repair anything, suddenly we've gone from about 25% over 30 years to over 50% of the pavements are over 30 years old. So you begin to think, wow, these pavements are getting as old as I am. We need to replace all this stuff, right? No, you can't afford to. But even 5 years makes a big difference. Back in 2010, the average age was about 20.2 years, average weighted on area and all. Step forward to 2015, if you haven't done anything, now the average age is 25. So you gotta pay attention to these things. And if we step forward to 2020, which is next year, we see with nothing being done, and some things have been done, so these are not exact, about 50% of the pavements are still over 30 years old. And some of them are over 40 years. Like that first runway I worked on, it'll be 46 years old next year. And they're taking it out a little bit at a time, because as they do some taxiway crossing, things like, they go ahead and take a piece out, because what's become a problem, and we'll see in a minute, they can't afford to shut it down. And we'll see why. Okay. So how did their pavement management program, you use a pavement management program to manage all this stuff. And how did it start? Well, I like to tell people it started very slowly at first. And when did it start? It started in 1984. So we have 35-year history out there that we'll talk a little bit about. And when we look at that, what had happened was in 1984, the fourth runway was about to be completed. So now you got 2 in the north, 2 in the south, great operational capacity. Someday, if we have time, we'll talk about the underground people mover, which allowed the airport to, if you had a plane here, and it was going to take off here, the original plans were going to have taxiway all the way down here, go up here and take off. Well, somebody got the bright idea, bury the underground, the people mover system as a, instead of an open ditch, cover it over. Then the plane that's down here can go straight up there, take off. And operational efficiencies was paying for the bonds as soon as the airport was opened, at least according to the airlines. So look at your ground operation, big deal. So the fourth runway is about to be completed. The runway, which is called 8 right, is primarily takeoffs. It's one of the 2 inboards for that. It was showing wear and tear. This runway is adjacent, and it's on the north side there. And it had been reconstructed in 1969 in 40 days and 40 nights, straight through. And hence it was always called the 40-day wonder. And I think they paid a premium of $5 million to do that, because when they did it, this runway down here was not in place. So they just had 2 runways and 2 crosswind runways, which have long since been taken out. So when you take out this runway, which was nearest the terminal, you really impacted operation. So they paid $5 million premium to do it in 40 days. We estimated that that runway probably had 5 million departures on it when it got finally replaced. So for $1 per departure or landing, they were able to do it in 40 days or 40 nights. Okay? Okay, we looked at that runway, 84. Hey, we're getting fourth runway. It had, 8 right had significant surface cracking, it has falls at the joints, and the longitudinal joints were keyways. Remember that. We'll talk about keyways in a minute here. Airport management was saying, hey, it'd be good if we took this out and replaced it before we get used to having 4 runways. And so everybody said, yeah, that sounds like a good idea. And I'm going to diverge on 3 tips to talk about here. Those are kind of design tips for you. But one is, don't use keyways. That's my personal preference. And we'll talk about why they don't work. But you know, you got a nice design keyway here. You can You see it outlined in red. Looks really great on paper, right? Very nice. But if we take a close look at that, we say, hey, there's a dimension there that's missing. Now, one might say, well, it looks like the dimension up there, so it must be that. But if you're on the project trying to get this built and arguing with the contractor, he says, hey, there's no dimension there. Whatever I built is okay. So you have to be sure you get everything covered. And the dimension here is missing, down to the top of the keyway. Now you can say, well, looks like that's almost at the level of the temperature steel, but it's not quite. So you got to be precise on what you specify, you know. And so what the angle, we know here, it's a ½ inch. This is 2 inches. We assume that's 2 inches up above because it looks symmetrical, but maybe it is, maybe it isn't. Okay. Why not use them? They don't work. That's very simple. Ernie Berenberg, I remember reading one of his reports in the mid-'80s that he had done some work on things. And he said keyways were fine until you need them. So that's kind of how they are. We look here, this is a longitudinal keyway. The female side is on this side, the male side is over here. This is concrete all placed at the same time. But look, why did that stop at the joint? What's so magical when I crossed the joint? And we pulled our hair out on this. We were studying this, and we'd take cores that were good in bad areas and cores that were bad in good areas. And we were scratching our heads. So finally I said, let's take an 8-foot long section out of here. So you can see the start mark and the finish mark, about a foot, foot and a half wide. We'll haul that back to the lab and we'll slice it up. And we'll map what this looks like on about 6-inch centers going down through there to see what we find. Well, things that we found they weren't built the way they were supposed to. Now this is a very good one here. You see, there's no problems in the surface that we can see, but here's where the keyway is supposed to be, and here's where the keyway actually is. Now if you envision a keyway, as soon as that slope, it opens the least little bit, now it's not in contact. You tie it and you say, well, it's tied together. No, maybe you have enough. Maybe you don't have enough steel to hold together. Maybe you don't put steel in. But these are things that you've got to look at. So they don't always get built as designed. Okay. So what do we do? Well, let's do away with the keyways and let's dowel the slabs all the way around. And we said, we think that might work. But conventional wisdom in the 80s, we were thinking, no, we dowel all the way around the slab, we're going to split it into quarters. We're going to lock it up and crack. Well, 30 years, fortunately, we haven't seen a problem. So sometimes your worries, you know, maybe you're looking to do something, go off a part of your airport or your highway where you got something that doesn't matter, build something and see if it works. The only problem is, you have 10, 20, 30 years to wait and see if it works or not. You don't always have that, okay? Okay, tip number 2, slab sizes. In the 60s and 70s, early 70s, Atlanta built for its runways and taxiways joint spacings that were 75 feet long. So 25-foot wide slabs, 75 feet long. Anything wrong with that? Anybody think? Well, slabs cracked it, 25 feet. Boom, boom. Almost everywhere you look. Those 75-foot long slabs became 325s. Say, well, let me fix that and I'll make them 50 feet long. And looks good, no cracks. What do you think happened?
Back at 25.
Back at 25 feet. So, you know, scratch your head and finally you say, hey, I think the concrete's trying to tell me something. If it's 25 feet wide, it probably wants to be 25 feet long. Now that's not in all cases. That's a rule of thumb, but it's a pretty good rule of thumb I've found. So we went to 25 by 25s on the runways and taxiways and doweled all the way around, except on aprons. Those are a whole different story. And with the runways and taxiways, with this issue, not a problem over the last 30 plus years. So it's worked. And other airports I've been at, Memphis and Charlotte, 25 by 25 has done well. So look at what's working at your airport or your highway and don't just jump on the latest fad, okay? If it works, don't break it. Now, tip number 3, make your geometry of your longitudinal joints fit what you need, what works. So the taxiways in Atlanta in the 60s, early 70s were typically 100 feet wide. FAA, as I was told, came out and said, well, we're only paying for 75 feet wide. Well, simple solution, just eliminate 25 feet, right? Build them 75 feet wide. I don't have to pay for the other 25 that FAA won't pay for. Well, that's fine. But what that does is my 3 25-foot wide slabs, suddenly on the main aircraft, the gears tend to go right down the longitudinal joints. And if they're keyways, that's an even bigger problem, okay? So you say, hey, going right down, it's highly channelized, I got a problem. How do I fix that? Because we had literally miles of cracked keyways on these 75-foot wide joints. We said, well, let's put 12 and a half, 25, 25, 12 and a half. And what that does, that gets the gears back more in the center portions of the slabs. Now, yeah, they've got to cross the transverse joints, but I'm not going down that longitudinal joint, particularly a keyway joint, with that. And we haven't built keyways since the 80s at Hartsfield. So this works fine. 25 by 25. Now you say, well, I've got a 12 and a half by 25. Remember my 25 by 50s, cracked at 25? Well, this crack at 12 and a half. They haven't, and what I think is occurring, it's just my personal thought, is this 25 is helping hold that 12 and a half together. That's at least my theory. But they've worked. And if I get cracks, transverse cracks out here, I really don't care because there's not that much traffic out there. So it doesn't matter. You know, most of the paving is to take up for the engines that are on these planes, not because I'm putting wheel loads. Get this right here. I'm not generally putting wheel loads out there except when I take off on the crossing taxiways or the exits. So in summary, keyways, be wary of them. Surely you guys aren't using keyways. How many are using keyways or think you ought to use keyways? Good, you get my vote. Slab size, 25 by 25 has worked. I know FAA likes these 15 to 20 and all, but those create other problems. I got more joints, more steel. Now on the taxiways, yes, I've got an extra joint because I got that 12 and a half on each side. But I don't have the gears going down the longitudinal joints. And joint geometry, like I say, keep it in the middle of the slab. Okay, back to the 40-day wonder. What were we going to do? We've just finished the north runway, and we're thinking about this one's not too good, and just what it was, it's 16 inches of concrete, had temperature steel, but it was plain, a moderate flexural strength, 650 psi, 28 days, third point loading. 6 inches of unbound aggregate base at 100% modified properly. 6 inches of soil cement with laboratory 7-day compressive strength of 400 psi on top of a prepared subgrade. And sometimes referred to as sandwich construction because this unbound base is quote loose in there, but it's sandwiched between a stiff soil cement layer and the concrete. And the theory being, well, that whole face is in compression across there. So an aggregate doesn't have a tensile strength, right? It has a shear strength if I got it on something, but up in the middle, it doesn't, when it wants to pull apart, it can. So, but we also had longitudinal keyways. So we're saying, So what we found was, when we went out there and looked, we had surface distress along the longitudinal joints, which were keyway. We have surface cracking in the interiors of the slabs, a lot of surface cracking. So that doesn't look good. John Culpepper with airport engineers had analyzed the traffic as best it was known and said, hey, in 15 years, from 69 to 84, it had already served 20 years of traffic. It was a 20-year design. So it's and we're going to complete the fourth runway. So it's kind of an open and shut case in terms of managers say, hey, replace this thing before we get used to 4 runways. What do you think we said? Anybody got an idea? No ideas? Don't be afraid. If you take my CE 498 class this summer, you will answer lots of questions, okay? And don't be afraid to toss something out. No idea is a bad idea, okay? So what we said is, hey, how about we do an evaluation program before you just replace this thing? One, if you're going to replace it, you need to know what conditions are out there to do a proper design, okay? So what do we do? Anybody got any ideas how you would investigate this? I'll pick on somebody if somebody doesn't have a suggestion. What's the first thing you might do?
Inspection.
I'm sorry?
Visual inspection.
What?
Visual.
You have to speak up. I was on a pile job, my very first job out of school, and I think it's now kicking in. So let me come close.
Okay, you do a visual inspection.
Visual. Ah, good. Yeah. And we've done that visual, right? We followed deterioration of the joints, surface cracking in the interiors, saying, hey, this thing's not in good shape. So we do a visual, and we'll talk about that in greater detail in a minute. But what we did was, after that visual, we came in with falling weight deflectometer. And in '84, that was a fairly new device for evaluating stuff. It had been out for about 10 years, but it hadn't caught on in the normal industry that much yet. But now you wouldn't think of doing anything, at least I wouldn't, without doing some falling weight deflectometer testing. We cut cores. We cored through the concrete. Now we have that unbound area base, and if any of you have ever been in the field, you can't dig that out very easily down even a 6-inch diameter core hole. So find your best technician with the core rig, and you core it out. You core it very carefully so that you don't lock the barrel in that hole. Because you're going to have a problem if you got your barrel sticking out and they say, hey, we got to open the runway for a plane that's got to come in on emergency. So you always got to be prepared to run and take everything with you. And then we cored the soil cement base. We did hand auger borings in the subgrade, and we did dynamic cone penetrometer testing. Now this was a dynamic cone that George Sowers at Georgia Tech had developed, but it's very similar to what's in use today if you go and buy one commercially. We did strength tests of the pavement layers, and we did petrographic examinations of the concrete, because we said we want to see those cracks that are in the surface. And remember, characterize your materials, no matter what. I've seen a lot of high-powered consultants come in, do a lot of non-destructive testing, and never take a core, never run a strength test, and they come up with wrong answers. See what's there. You may find out the pavement's thinner than you thought, or thicker than you thought. We once were in an airport. We had done all the pavement management input for them. We'd researched all their files. This runway that was having some issues had 16 inches of asphalt in it. But when you looked at FWD data, it was pretty strong. You know, why does this thing have a problem? When we took cores, I found out they had 24 inches of asphalt. Hence, that's why the FWD data looked as good as it did. So take cores, look at your materials. Okay, we did the evaluation of 8 right in the summer. Weather affects your results. If you do the testing in the summer, or in the spring or fall, or in the winter, you may get different results. And we'll talk, if I have time, about one. What we ended up finding was, even with dowel transverse joints that had 85–90% joint efficiency based on deflection in the summertime, we had areas where they would drop to 10, 20, 30% in the wintertime. So the joints open up. You say, well, I got dowels in there, 1¼ inch dowels and 12-inch studs. They're still flopping in the wind. Well, I brought a little piece with me to show you why some of that happens. Okay, so we normalized the FWD data to 25,000 pounds so we could figure out, we could compare all the data against itself. Stiffness of the slabs typically averaged about 5,000 kips per inch. So it was a decent structural number. Joint efficiencies, summertime, typically 85–90%. That's the deflection of the unloaded slab divided by the loaded slab. Very simple way. We didn't get into all this determining it by stress and all those issues. Surface cracks, when we did the petrographics, they went down about 3 to 5 inches and stopped. And so, well, that kind of maybe helps explain that there's still a lot of integrity in the slab. And what we ended up feeling that we had was likely it was early age shrinkage, drying, maybe thermal, because the cracks would go down. They tended to go around aggregate, not through the aggregate. So that tends to tell you either I got poor bond between the paste and the aggregate, or the crack probably occurred fairly early in that hydration process. And we had some ASR, good old ASR. Seems like you find it everywhere. But it was very low severity, and we had some dark rings around the aggregate, but no disruption of the paste aggregate interface. So, okay. What were our recommendations? Anybody want to make a recommendation? You got enough data to make that engineering judgment? In fact, you probably got more data than you'll have on a lot of jobs when you get out there. Who wants to make a recommendation? Nobody? If you came to work for me, you're fortunate I'm retired. Although, but if you came to work for me day one, I'd probably put you on this job. You'd be working maybe as a technician, so you understood everything that was going on. But I'd haul you in and say, okay, here's the data. You're from this great University of Illinois. You've had the best professors there are in the world, the best education. What do you recommend? Now you got to pay the piper, so to speak. You got all that knowledge. How do you apply it?
Do we know the traffic?
Huh?
Do we know the traffic once it opens?
It's had 20 years of traffic in the 15 years it's been open. So anybody, how many vote to take it out? Nobody? How many vote to leave it in? Why are you voting to leave it in? Because you think I left it in, right?
I'm assuming the results are good, right? We haven't seen the results.
Well, I've got good structure, I think, with 5,000 kips per inch. But I got a lot of cracking. I've got deterioration of those longitudinal joints. They're keyways. What do I do?
Yeah, we'll say just leave it for a little bit.
Leave it for a little bit. How much is a little bit?
I would say a couple of years.
A couple of years,
2 years.
okay. How many vote to leave it in for a couple of years?
I don't like that.
Just time? How many would leave it in for 10 years? Or 20 years? Anybody want to vote for 30? Nobody? So I'm assuming only one person with 2, nobody else the rest. The rest of you, even though you said you weren't going to take it out, are going to take it out, right? Fairly quickly? Airport management wants you to take it out. You're a consultant. Hey, I got a big design project here. I get a lot of fees and do stuff.
Cracks are limited. The structure is good. We'll do something for the top rather than taking it out.
Okay, do something for the top. Put an asphalt overlay on. Cover up those cracks. Okay.
Rubberization.
Well, call Marshall? Yeah, call Marshall or Ernie. They'll tell you the answer. And I called Marshall before. Hey, Marshall, you know, what do you do here? I need your help. And he will give you a good answer. I can attest to that. What we ended up saying was, hey, we think it's good for 5 more years with some nominal repairs. And there's no exactness to this. We said replace 10 to 15 slabs, full depth. They ended up replacing portions of 2 slabs to full depth was all that was done. Seal cracks that are greater than 1/4 inch wide. Repair the longitudinal joints with a special block type repair. We'll talk about that under maintenance. And seal all the joints. I know there's a lot of arguments. I think I happened to see Dan Zollinger's video from last week and the discussion about, well, leave the joints open or don't leave the joints open. When I was graduating, Harry Cedergren had just done a study, and he said that water going over a crack or a joint, if there's a place for it to go down below, 70% of it will go down below. That number's just always stuck in my head. So seal the joints is my philosophy. And they hadn't been sealing them, so we said, hey, because water's getting in and water damages the paper, no matter what. Even in Atlanta, we get some freezing temperatures, so you do get freeze. In fact, we get a lot of freeze-thaw cycles. They're shallow, but there are a lot of them. So, you know, we're beat on ball-peen hammer, where you come up here and you get a long one that stays for days. So, okay. And let us come back in 3 years and see what we've got. We know we've got 1 point on performance history. This thing was built in '69. Now we've got some 1984 data. Let's come back in 1987 and see where we're at. The airport loved that because they didn't have to do anything. Put all that money in the bank or put it on something else. So, what went beyond that? They did their repairs, things chugged along. We've gone back about every 3 or 4 years since '84 and performed testing again, and we've done it on the whole airport, not just this runway. We did testing on the rest of the airport, but we archived that data for future use because the focus was on 8 Bright. But about every 3 or 4 years we go back, and I think they went back in 2016. The guys came to me, I was retired, said, hey, we want you to work on this, give us your resume. And I said, oh man, that'd be great. And I said, what in the world am I thinking? You know, I'm retired. You guys know what you're doing. Hopefully I've taught you well. Run with it. And I also had I felt a bias because we're going to be looking at my runway, if you will, the one I dealt with in 1974. And I'm going to be biased to leaving it in. And I said, well, I'll not inject that bias into it. So they did it, and I don't sure what they ended up doing because I said, hey, I don't want to know. Okay. But, so we go back every 3 years and give it 5 more years. John Culpepper, with the engineer, said, hey, this is great. We call you up every 3 years and we get another 5 years. Okay? So, and remember, failure is like beauty. It's not an exact line in the sand. It's more like a paintbrush. It's in the eye of the user. Okay? Yeah, you can do all these nice, fancy, very precise calculations, but at the end of the day, that may or may not be the issue. And it was replaced in 2006. 37 years old. That's 22 years beyond when they would have replaced it if we'd said replace it. It was operational issues. Ben DaCosta said, hey, 5th runway that we talked about, just been completed. We will replace this runway before we get used to having 5. And I was kind of depressed because, I'll show here in a minute, I was hoping to get to 40 years. But, you know, can we do that? So, as I said, we've been back numerous times, and each time we try to add new and latest evaluation testing techniques. Now remember this in your career, I've never found one test procedure that answers all the questions. Normally you've got to do a variety of tests and see where they kind of come together, and do they give you the same answer? Because like I say, you go out and run all kinds of NDT testing and say, hey, this pavement's either really great or hey, you really need to replace it. And when you do your material characterization, you may find just the opposite is going on. So you have to look at that. Okay, so what do we do over time? Well, one of the things to remember too, after we saved it in '84, they replaced it before we get used to having 4 become, we can't afford to replace it because we can't shut down to do it. Okay? So sometimes you back yourself into a corner and you're stuck. So always look out. What's the consequence of this and that? Remember your systems engineering? Most of you have taken systems course, I assume, where you draw your T-diagram and the different things that can occur, the probabilities and the severities, and figure out, well, which ones. Normally in practice, you don't get quite that exact. It's kind of, there's a lot of, like Ben DaCosta said, you will replace this before I get used to having 5 runways. I said, yes, sir, you're the boss. Okay, these are just a summary of a lot of the tests that have been done over the years and when they were implemented. And if you go back to the start in '84, we did visual surveys. We did those first so we can see what we've got. We did FWD. The FWD became the HWD in 2001, and we'll talk about that. we looked at cores and borings, lab tests, we did concrete studies, and we started developing a photo history. Very critical to assessing what's going on. Okay, so 84, we walked the runways, and we started taking photographs and filing them away, and knowing where they were at. In 1990, I keep hitting the wrong button. In 1990, we formalized the PCI procedures. Said we need a number. Let's do what's out there. It's been around for quite a few years. It was accepted, so we started doing that. In 2001, we started putting the data in micropaper, but all this stuff is great, but get out and walk the pavement. You know, people may bring all the data to you. You can fly your drones. You can see everything from your office. Get out and see what you see on the pavement surface, okay? So PCI, we kind of got down to where PCI was one of the driving forces in the decision process. And this just shows runway 8 right, and this is the 2004 study. And we show here the PCI data for the various sections going down the keel. We call it the CD line, but that's the 2 slabs of 25 feet in the middle. And we see, wow, we chose 50 as a problem. So other airports might choose 60 or 70. So you got to know where is your criteria at. And we said, hey, around 2010, we think you're going to have really significant issues. But we should be able to make it to 2009, which would have given us, hey, 40 days, 40 nights, gave us 40 years. However, as I said, it got replaced in 2006. But it could have probably made it out here to 2010. Yeah, you're going to keep your eye on these areas here, maybe go in and do some spot repairs to stretch it out to that. But a lot of times these decisions are made not in a highly calculated process. In 2001, we automated digital mapping. Drive down the runway 40, 50, 60 miles an hour, doing it at night when there's little or no traffic, and get about a 13, 15-foot wide path, and put all these things together, and it was just almost as good as walking the runway. You still want to walk that runway even when you do this. Okay? And if you look at some of the things here, these are just pulled out of some of the files. 2001, 2004, these happen to be the same spot. Part of the problem with the digital mapping, being sure you can find what it is you're looking for. This is a couple 3 square feet out of 1.5 million square feet. You know, so how do I find that one in my 2004 file? Okay? But you can look and see that in 2004, yeah, those are the same cracks. Looks like the crack's getting a little more pronounced up here. You look, you can kind of see one there. See, it's beginning to grow off here where it doesn't appear to be there. And same here, this is another spot, 2004, 2007. You see, and actually 2007 looks better than 2004. But lighting and some of those things impact your assessments of these. So be careful when you look at those things, okay? And I always thought, well, we're looking at the pavement through a microscope. Good thing, get your IT people, paste all these images together in one big file, go into a big room like a conference room at a hotel, big ballroom, get a big screen and project it up on the wall, and you can see a lot. You know, you can just walk down that runway in that room and pick the spots that you then want to go out and look at for sure on the pavement, because they may say, hey, we're only going to let you out there for 30 minutes or 2 hours on Saturday morning. I can say, and I think with pretty good confidence, I'm the only person that's walked all 4 runways in Hartsfield when we had 4 runways in one day. And I've done it 3 times. So people walked it one day with me, but none of them walked it 3 different times in those 3 evaluations. Now they'll give us 2 hours on a Saturday morning. So it's kind of like, hey, give me the old days back, okay? 1995, the airport started sending out an engineer, GPS on his back, or her back, sounding the pavement, mapping the cracks, and creating these map cracks. And the beauty of that is I can now take, you know, a 95 map, and look at a 98, at that map in 98, and see, do they look like the crack? Are there more cracks? Are they growing? What's happening? And with all the fancy tools we've got today, you know, okay, I can digitally map the lengths, map the widths, and put more numbers on them to understand what's going on. Okay? And you sound the pavement. Rebar keeps your arms going, but it'll give you pretty good chain drag. Okay? And in 2007 on, Hartsfield was spending about 50 to 100,000 per year on its two oldest runways, 8 left and 9 left. Okay? Okay, falling weight deflectometer. Most of you probably seen that if you're working out here. In '84, we started with 25,000 pounds. In 2001, we went to the heavyweight, and I think you all know the details of that, 12-inch plate versus 18-inch plate. I like to look at the joints. Longitudinal joints, transverse joints, corner joints. Look at those deflections and joint efficiencies, okay? And we can back calculate and get a lot of numbers. But you can back calculate a lot of bogus stuff. I see people in their reports putting out, oh, the back calculated modulus is to the nearest 1/10 of a PSI. And I say, are you kidding me? Maybe to the nearest 1,000 PSI, okay? But when I see that, I immediately say, that person doesn't understand the real world. And I kind of write them off, okay? So, but you can estimate things, and again, get another number that you're putting with all these different factors in to see what do I think is going on here. Okay, in '94 we started Right Quality. Tony Girardi came in with his equipment. He sets up a laser device, spins around a plane of light. He's got his rolling cart with his sensors on here, and every foot going down and we go down the wheel path, he gets a reading, and we can then plot the profile by the foot. You know, should it be 6 inches? Should it be 3 feet? Hey, I don't know. You try it and see what you get. 1 foot seemed to work pretty well. And he had done a lot of this when he was at, I think it's Wright-Patterson up in Ohio, that, you know, how much acceleration, what roughness of pavement makes it too rough that it can black out the pilots. That's where a lot of his stuff came from. Okay, then we can look at that and see what's the ride quality. This happens to be runway 8 right in 2001 and 2004. And that 2004 study, we're saying, hey, we're beginning to see ride quality drop. It's not precipitous, but it's dropping. That's part of, we think, by 2010, you're going to have a problem. Okay, coring, boring, sampling, lab testing. I can't say enough about it. Yeah, I come from a testing background, but I was part of helping Marshall on the research project way back when, building his, we called it the Blue Goose, but you know, the pneumatic 4 at a time test for resilient modules. Get those strength parameters. Now you still have the problem, what do I put into my models? We got great models, but material characterization input, that's still a tough go. But we ran tests. Sometimes you take unusual samples. Here we had a problem with some curling issues. We took 26-inch diameter cores. I called a friend who worked in the caisson business. He said, hey, can you take about a 24 to 36-inch core for me? That was about the most it could get lifted out with easy equipment that we could get. He said, sure. So we just bring out a core barrel from rock coring in caisson rig. So it worked out well. So we cored it out, took it out, and we'll talk about that in a minute. Take your cores, line them up, you know, across and see, hey, what's the thickness of the concrete? What's the thickness of the CTB? And oh, by the way, that CTB is a little bit variable. And my soil cement isn't always there. What you think is out there isn't always there. You know, in the middle, in the heat of battle, when they're building the pavement, they come to a soft spot. What do? Do you go back to the office and redo the design? No. If you're a good field engineer, you say, hey, undercut 12 inches and put in crushed stone, or undercut 6 inches and just make it concrete. So sometimes that's why you find that somebody made a field decision because it was going to cost a whole lot more to go back and do a fancy calculation than just doing something that experience and engineering judgment tells you we'll be okay. Okay. Moving right along, and then we ran split tensils and modulus values. And in 1990, we instituted resilient modulus testing of the subgrade. We'd kind of been playing around with it because when I got control of our lab, soil lab, I made them build a one sample, one pneumatic device that we could test on. When we got involved with the sharp testing, we were told, hey, you can get the contract if you'll buy a servo-hydraulic device to test with. So we said, no problem. So we got into the 21st century, late in the 20th century. Microscope, take your core that's not tested for strength, generally slice it vertically because you want to look from the surface down in, polish it smooth as glass, and look at it under a microscope, 10 to 60 x. Look for cracks, presence of material in the air voids, reactions, ASR. Do you see issues like that? In 2004, we added scanning electron microscopy and energy dispersive X-rays. Again, we're able to go in and look at what are some of the materials that are really in there and what kind of concentrations do they have, right? Again, able to put some numbers on. Photographic documentation. Now, in the old days, you went out with your camera, took a picture, sent it off to the photo developer. Maybe 2 or 3 days or a week later, come back and say, oh, it didn't take. Not what I wanted. So today, I go out there, I take a picture, I know instantly if my picture's any good. You guys have got it a lot easier these days, okay? Because as Terzaghi said, you may only get to go to the site one time. Collect everything you can. Life's a lot easier these days, at least I say. This is a patch done in 1990, photograph of a patch. One of those on 8 right that was done. This is the same patch. It's hard to see because of the lighting and there's been some rubber removal that makes it look a lot nicer. But that's a patch that's probably 20 years old right there. So yes, you can make long life patches, and we'll talk about how we do that. And some cracks that look about the same. So, at the end of the day, what was happening? PCI primarily drove things because we had good structural capacity. We looked at ride quality. And what we did was we put things on a chart. So we kind of see how do those line up. And so we have up here PCI values, and we say, hey, on 8 right, I'm not sure if this is 8 right or not, but anyway, we can look and say, hey, we're knocking on the door of the problem zone with this. So you begin to say, I think I'm beginning to have a problem. I look at my stiffness modulus, I look at my longitudinal joints, and I say here, I'm knocking on the door of critical parameter that was established. And my ride quality, same thing here. I'm beginning to get into the mild roughness to the moderate roughness. So that was kind of what we said, okay, we think we'll get to 2010, or we think it'll go through 2009. You ought to be looking at major rehab or replacement in 2010. Not an exact science, okay? Okay. So that's how we said. When would you do it? Well, they said, hey, we want to do it before we get used to 5 runways, okay? They replaced it in 60 days. Interestingly enough, the value for operational delay, the airport valued at $15 to $20 million. I think it's a whole lot higher than that. The airport guys once told me they value delay at the airport at $50 a minute on construction jobs. That's $3,000 an hour. That just doesn't sound high enough to me. I'd be more like $50 a second, maybe. But, okay, so what are the keys? We've got a long history, 34 years. We've had good performance. We've got data specific to ATL, not some other airport. Because construction issues are going to be different than other airports. You may have different PCI curves. A whole lot of things may come into play. Longevity of personnel. We were out there for 40 years. We were on this for well over 30 years. And the people that have taken over have been working with us for the last 10 or 20 years on this. So there's a lot of continuity of things. And we extended 8 right, 37 years, 9 lefts, 44 years, and still going. And back of the envelope with one of the planning people for the airport, $100 million in capital costs saved because we skipped 2 cycles of replacement on 2 runways, okay? A lot of money. You say, hey, can I have 1%? That doesn't work that way. Okay, quickly, I got a couple minutes. I'll go through 2 major, because there's a couple of things I want to show you here. Emergency repairs and annual repairs. 2007, they went to an annual program. They used to do it every 2 or 3 years, and they spend $2 to $4 million a year on that billion or $2 billion or $3 billion investment. Typically, it's focused on joint sealing, crack routing and sealing, spalls, typically at the joints, utility conduits, trench drains, and some full depth slab replacement. These are what some of those look like. These are some corner spalls and some crack sealing and routing, or routing and then cracking. This is that block type repair that I talked about, the special. Frank Hayes was really the guy that developed this, and we worked together with it, but he was the genius behind it. But this is a spall repair at a corner, a joint here, a joint here. So you cut the concrete here, and you cut it here and remove the bad stuff. Bush hammer down. Everybody knows what a bush hammer is, right? Bush, like a jackhammer, but it's a bush hammer, not a jackhammer. Clean it down to sound concrete, blow it off, clean it dry. Be sure that these joints are sawed smooth. Then drill back at a 45-degree angle into the good concrete. So this goes down. That then bar is epoxied in, and then it goes horizontal as it comes across the patch zone. Then drill vertical bars down into the good concrete, epoxy them in, and use them to mount the interior reinforcing steel to those, so you reinforce the patch, and then use a fibrous concrete when you go back in. High strength, because these are done at night. They got to be open to traffic 6 o'clock in the morning, so you're looking for a reasonable strength gain in 3 to 4 hours. You say, that's a lot of work for a patch. Remember the one that I showed you? 1990 to 2004, I think it was. 14 years, look good as new. At least I'm a little biased, but look good as new to me. It works. This is what it looks like in practice. Be sure to use fiberboard where you want to maintain your joint. A lot of times I've seen people patch and they put it right up against the other concrete. It bonds and cracks away. So make sure to maintain your free, but you can see here, these are the angle bars dialed in, going straight across. These are the vertical bars, and then this is the reinforcing steel. Yes, it costs more than the typical quick slap some stuff on their patch, but lasts a long time. In fact, coming over this morning, I had a discussion with Jeff. They were talking about how long the patch is supposed to last. Think about that. He might have that as a question on your next test. Okay. Remember, concrete moves around. Can I go a couple more minutes?
Yeah.
Okay. 100 feet of pavement, concrete pavement, will move about 1 inch when I change the temperature 120 degrees. Does the temperature change 120 degrees here in central Illinois? I think so. I think what you had some 20 below zero this last winter, and you're going to be 100 this summer. So yeah, you easily get 120. To say nothing of the heat absorbed by the concrete. So easily you get that, put in a normal CTE, coefficient of thermal expansion, and you easily can get maybe 3/4 to an inch. So 25-foot slabs will move 1/4 of an inch. We don't want to seal the joints when I'm doing new construction. Raise your hand if when I get the season that you would seal the joint on new concrete pavement. Winter? Okay. Spring? Nobody in spring? Okay. Summer? Nobody in summer? Fall? Okay, so I got 2 in winter, 3 or 4 in fall. So nobody in spring, nobody in summer. What's happening in summer? Joints are closed up. So if I seal, come wintertime, boom, they're going to open a lot. If I do it in the wintertime, wait, did I say wintertime? No, summertime. If I do it in the wintertime, the joints are open, and come summertime, they're going to squeeze the stuff out. So I like to do it in the spring or the fall where at least maybe I'm in the middle of the road for thermal movement. Just a thought when you're thinking about that stuff. Concrete never does what you always expect it to do. There's a whole host of factors. I remember Dan was talking about things last week, and all these come into play. And I once had a job in New Mexico, contractor, actually it was called by an insurance company. They said, contractor's claiming wind damage to his pavement. And he's doing it under his builder's risk policy. The owner had made him buy a builder's risk policy, which typically you buy for buildings, because the wind comes along, blows the building down, insurance pays to reconstruct it. This was on concrete pavement, slab on grade. And so he claimed under his builder's risk policy, wind damage to his concrete because it was cracking and the owner was making him replace it. And to make a long story short, he said, well, this is the worst weather there's ever been for this type of stuff. You know, the sun comes up, humidity drops, the wind starts blowing, the temperature gets hot, all those factors are negative. So there was a weather station at the end of the runway almost, looked at 10 years of previous data, and guess what? That year fell right in the middle of the previous 10 years of data when you looked at all these different factors that you could get the data from NOAA. We said, well, it's not the worst year ever. And the insurance people finally had to decide, well, they're going to pay or not because they were out selling these policies. Not that many of them were being required. And should they pay or not? Because if they didn't pay, they'd get a bad reputation. Okay, this is an interesting one. This is a taxiway. Outbound taxiway going from right to left, and the only place in the airport where we got several corner cracks like this in the center slab. This is 325s, and the center slab right where they are going. So we said, So we're out there on a cold February morning, and Frank Hayes was telling me, you know, I hear these clicking sounds when I'm out here sometimes on cold morning. So when the plane goes by, I said, well, that's kind of strange. Luck would always have it. A lot of your engineering solutions are purely fortuitous. The DC-8 had just landed, and we called the tower and said, hey, ask the Delta pilot if he'll taxi down another exit, come back and come along where we're trying to look at this problem. And the pilot was kind enough to do it. So we stood back at the edge of the concrete. The plane's going slow, so the engines didn't blow us away, as you see in some of the movies. And lo and behold, center slab, the corner, went down, came back up, and it wasn't cracked. So, wow, concrete's not supposed to be doing that. So let's see what's going on. So we did an investigation, and we did a core. This core happens to be about 5 feet back from the corner of that slab. You look down the core. I'll get this right about the time we get done. That's the concrete, and yeah, you got a few bug holes, but that's old film box that the film can comes in. Slid between the CTB and the concrete. And it's about an eighth of an inch thick there. And I said, I got to see more of that. How can I do that? Well, I could cut out a big square, but then that gets a little hard to fix. I said, my coring buddy, cut that 26-inch diameter core. So remove the joint sealant and pour epoxy in under gravity flow because we didn't want to pump anything and disturb something. So we said, we'll lock it in place as it is, and then we cut the big core, and we look under, and lo and behold, this is the longitudinal joint here, so this is a slab that's on the other side. This is the corner that was moving, and look, there's a 3/4 inch void on the other side of the longitudinal joint. No wonder the slab was going up and down, and it just hadn't fatigued yet. And it was, interestingly enough, cracking the CTB right beneath the transverse joint, and my argument is I'm pretty sure the concrete cracked like it was supposed to and took the CTB with it, not vice versa, okay? Because the odds of that CTB cracking there and being right under the joint, pretty small. So what do I do now? So I call up my coring buddy again. He said, hey, I can mount a portable saw on top of that core. It's big enough to do it. So he mounts a portable saw on it. We slice out about a 3 to 4 inch thick slice that's got the dowel bar in it, okay? And as everything would have it, lo and behold, one of the cuts, we found a styrofoam coffee cup at the bottom. Now that coffee cup has nothing to do with the problem, but you find things all the time. So I said, So I talked to our guys in the NDT department, NDE, and said, hey, let's X-ray this slab I've got. I want to see what that bar looks like. So they played around with the exposure times, and yeah, even here the bar is straight across, but the burn of the radiation makes it look like it's been burned out. But if you look real close, there's a light gray area there and a light gray area right there, which are about 1/16 of an inch voids on top of the joint on the upstream side, on top of the dowel on the upstream side, and on the bottom of the dowel on the downstream side. So as this slab pushes down, it pushes this against the concrete and leaves the void behind. Okay? Okay. So we said, our 12.5, 25, 25, 12.5 would be the replacement. Contractor does that. He beats on it with a panic ball to demolish it. We get a call and say, hey, the slabs we're trying to leave in place, that 12.5, the bottoms of them are all broken out. The contractor said, hey, it's vibration. So we come out, we measure some vibration, and it's well below 2 inches per second. So we say it's not vibration. And so what was happening was, he was getting so close to the saw cut for us to come out that the concrete bulks when you break it, and as it's being pushed down, it's just shearing the bottom off of that slab. So we said, cut another foot out and keep that headache ball at least 2 feet away from the joint. Problem went away. But now we have two 26-foot wide slabs, not two 25s, okay? And one of the things, well, full depth replacement, 22 inches of concrete, because we got to take out CTB. So, well, gee, I don't want to put CTB back in this. It's about 1,200 feet long. Let's just put in 22 inches of concrete, one operation, boom, we're done. And to try to compact CTB in there would have been very difficult. How do you get up to the edges? Looks nice and neat on paper, but go out in the field and see how close they can get that roller to that concrete. They don't get it quite there, especially when you're not looking. PCI, even in 2014, was still 66, okay? And I'm out of time here, but this was a concrete pipe, didn't get cut off or didn't get plugged correctly during construction, and void ended up occurring under the slab. They had problems when they went out and investigated. This is the core, concrete core, that's laying in a 25-inch deep void beneath the slab. It's on top of the CTB in this particular case, and it's hard to see in this, but the core is laying on its side. It's 16 inches of concrete, fell down, laid over. So come back, take it out full depth, that's what some of it looked like. One, plug that pipe off so you quit losing soil in it, put in a flowable fill, get it up close, compact in sand screenings, and put it together. And with that, I ran over my time, apologize for that, but hopefully it was of some value to you. And Jaime, I'll turn it back over to you.
We have a couple of questions.
Charlie, you ever had any fog problems at Atlanta?
Not that I'm aware of. They do have periodically, they get people that are working for the airport to go out and walk the runways and find stuff, pick up stuff. I know I've seen bolts out there. You know, occasionally you'll see a nut off of a plane or something.
Concrete spalling?
Huh?
Never.
There's not been one that I'm aware of. It's out there, but they seem to be able to take good care of it. They don't get it all, but as far as I know, we've never. The only time there was a FOD problem, this is a story for another day, but I'll just real quick. There was an underground pneumatic line that one of the airlines, Old Republic Airlines, used to run the engines, or turn the engines on the plane so they'd have power, so they didn't have to run. And that was put in, ran around the south half of Concourse D. Well, that line failed and it sucked the sand backfill into the pneumatic line and pumped it into the engine of this one plane, which was a big problem. That's the biggest, I guess, FOD problem that I'm aware of. But surface problems, knock on wood, I think they do a pretty good job of surveying. And generally, things are pretty good out there. I mean, yeah, you'll see some stuff doesn't look too good, but it's been good over the years. Other? This is.
It was an excellent presentation. So in the 8R project, what was the outcome of the ASR investigation? You mentioned well, in the 8R.
Right, yeah.
What was the outcome of the ASR investigation? Did you observe it?
The ASR was a low to moderate issue. It never became an issue. it's kind of laying, and yeah, a little bit, but it wasn't spoiling the concrete per se. It was even, to call it moderate is probably too high. And I remember when I went to the airport, I was doing concrete mix designs back in '74 for the contractor. This was when, before things got really legalistic, and you did a lot of work for all the parties on things. But I was reading through the specs, and it didn't require low alkali cement, but this DOT did. And so I don't think they had been using low alkali cement. Now, runway 9 right, we took it out in '99 in about 35 days, and our recommendation was there, hey, we don't know when the ASR is going to become totally unacceptable, but you really ought to replace it. And so that 9 right on the far south side was taken out due to ASR. 9 left has a little bit of it, but when I look back at the old mill reports for that job, while they didn't specify low alkali on 9 left, they got the equivalent of low alkali based on the mill reports for the cement. So they lucked out. They've got it on 9 left, the runway I worked on, but 44 years, it's still hanging in there. And when you get to 44 years, 45 years, you say, hey, we did pretty good. We probably over-designed, but that was okay. It saved a whole generation of replacement, to say nothing of operational costs, user delay, and sustainability issues. So, yes, Barry?
It looks like design is getting to be more than just thickness nowadays. You know, you got the problem of not only the quantitative but the qualitative things. How do you get this qualitative stuff into your design? In other words, the problem, you know, it's not just thickness anymore. It's compatibility. It's a whole bunch of things.
It's a case of, you know, everything seems to be driven on thickness, but thickness isn't the issue. In fact, I did some analysis way back when, using the old FAA procedures, no fancy finite element or anything. And I said, well, if I've got 100% joint efficiency, I only need 14 inches, based on the FAA at that time. I've got 16 inches with dowels that we subsequently found out weren't always working well. And when you take 16 inches and 14 inches and look at the moment of inertia that puts in, that pavement line goes way up. And so what it's kind of been was 16 inches has worked fine. It's probably more than they need, but it's worked fine. This is the busiest airport in the world. You can't afford to shut it down. So they just stick with that. And the issues, and we covered some issues earlier, I think, before you got here, of joint spacings and geometry. You know, the 12.5, 25, 25, 12.5 came on taxiways, where with two 25s in the middle, we're putting the gears in the middles of the slabs, if you will. So that's a qualitative issue that I can't really quantify in design, but my common sense just tells me, hey, if it's in the middle, that's better, because the way I tell people, look at it is, okay, if I'm in the middle of the slab, I've got two sides holding me up, versus if I'm at the joint, I got one side holding me up and maybe a little bit from the other side. So that's a bit of the quantitativeness. And like the 25 by 25 slabs, as I showed, the 25 wide by 75 feet long, got 3 slabs with time, cracked 25 feet. So they went to 50 by 25, got 2 slabs, 25 by 25. And they said, hey, concrete's saying 25 by 25. And that's where the 25 by 25 came from. With the ASR, the airport has done some studies. They're using lithium in the mixed designs now. They're specifying low alkali cement. The patch repair, you know, if we do get a problem, we go back with that patch deal that, yeah, looks like it costs a lot of money. But those things last 20, 30 years. So I can't really answer your question, but you just kind of comes together, but it's not a number. As I said, failure is a paintbrush. It's not a line. So anyway, long answer to a short question. Yes?
I was curious, how do you schedule an evaluation, like an evaluation of the pavement if it's the world's busiest airport?
Oh, you do it at night?
And you use that device with the light? Because the way
Oh yeah, well that
people
works
see-
best at night anyway.
Okay, so okay.
So that device at night is fine. The falling weight deflectometer you can do at night. The coring, you've set up lights. At Hartsfield, you're lucky because typically after about 11:30 at night to about 6:30 in the morning, it's pretty low traffic, and they can shift to the other runways, particularly now that they have 5. Back in the old days where we had 3 and then 4, it was a bit more of a juggle. If you go to Memphis, there is no graveyard shift, as it's called. FedEx comes in there all night long and goes out all night long, and we would get maybe 2 or 3 hours, maybe from midnight to 3. And then it's, hey, get off at things. And so you factor that into your pricing. You know, hey, I'm only going to get 3 hours a day instead of 8 hours a day, but I still got to pay the crews for 8 hours. And now suddenly a 2-week job is 3 or 4 week job. So everything's a little different. The Memphis is probably the hardest airport to work at because FedEx, well, and is it Lexington? Where UPS is sometimes difficult. I think it's Lexington. Yes.
So similar to FWD, I mean, ground penetrating radar is also another NDT technique.
Yeah.
But I didn't see.
We haven't used it. We could. We probably should. There's just a whole host of things that you ought to bring because obviously with ground penetrating radar, I can get a lot of data. And what I really prefer to do with non-destructive techniques, one is go out and do that visual survey. Walk that pavement, see what you got. Then figure out, okay, what are the NDT techniques I'm going to use? Get a lot of data and then analyze that data to say, where do I want to put my destructive tests, my cores and my borings to run my materials testing. And yeah, the radar, we should be using it. We just haven't. The guys may have picked it up since I've left, but we played around with a lot of things over the years. And once you find stuff that works, you're slow to change, and that's always a problem. Because if we hadn't changed from '84, we'd be getting a lot different answers today than as we let it modify. So, you know, as you all develop new techniques, industry's out there like, hey, how can I apply this technique to what I'm trying to do in the real world? Okay, yeah.
So regarding the project you were talking about that you looked at for 3 years and then left it for 5 years and minor repairs. So every 3 years when you visited the airport, what kind of repairs you did? You just the fixing of the joints and sealing the joints. So when you mentioned about like what should we do in the case of
Right.
So the solution was like sealing of the cracks and sealing of the joints so
Right.
that water doesn't get into it. And we looked every 3 years and it lasted for 40 years. So so every 3 years you did some repairs or you just watched it like?
Well, what was done, we'd go out every 3 years to look at the
Yeah.
main picture
Yeah.
thing. And you'd always find, as I say, they've got the emergency repairs, which those are obvious. You got something breaks you out and fix it.
Yeah.
The annual program was being done every 2 or 3 years.
Okay.
And then in '07, I guess it was, they started doing it every year. And so they have a program where they have a contractor on retainer that knows what to do, and they tell them where to go out, use the standard fix like that. The rebar drilled back in and all. That was a generalized drawing that tells you the spacings of those things, no less than 6 inches, no more than 12 inches, these things. So you go out and you look at what you got, and you say, okay, boom, 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 but you got the criteria. But you want to do it, you want to do things every year, particularly in an airport like this. And you may want to go out there 2 or 3 times a year and look at things and just be sure what's going on. But once you've been there for a long time, I don't want to say you get complacent, because that's the #1 enemy of engineers, is complacency. But you know the airport. We have one slab, we call it the Charlie and Frank slab, but this was on taxiway B on the north side of the 40-day wonder. And you'd always bring some high-powered consultant out there and show them this slab. And it was 2 slabs, they were interior, they were the centerline slabs on a taxiway, where every plane up until midfield was open came up, stopped, and then they would pull across that to pull out on the runway and take off. It's just cracked like crazy. I mean, the spacing's probably 2 or 3 inches. So you bring that out and ask somebody, well, hey, what do you think about these 2 slabs? And the normal person says, man, that needs to be taken out this afternoon. Don't wait till tomorrow. They have submitted. we think, because Frank and I weren't there in '69, that it was the last two slabs placed in the '69 work because it's dark gray, so it looks like it's been juiced up with a lot of cement. It's darker gray than anything else. And so what we think, again, this is just suspicion, they put a lot of cement in it to get strength so they could open it on time. But it's just cracked like crazy, and you know, it was there until that runway was replaced in 2006. So, but you bring it out, everybody says, oh, that's got to come out. Well, been there for 30-something years. Did okay. Yes.
Yeah. So I have a question for the runway. So we know that the probably runway can be divided into probably three parts. The plan which is accelerate and deaccelerate, then another part that can touch the ground or leave the ground. So did you see like the cracks are different in these three areas?
Well, you'll see different crack patterns, but it's not like the ends are more cracked than the middle, or the middle's more cracked than that. The cracking, the PCI tends to scatter all around. What we did was, we had three lines going down the runways. We call it AB, which were the two outside 25-foot slabs, EF, which were the other two outside, and then the CD, which were the keel section, the middle 50 feet. That's where we really look in because that's where the planes are landing, that's where the wheel paths are tending to go. And then it was divided down the runway, looking at exit taxiways and traffic patterns that way. An interesting thing on 8 right was it was faulty. Even though those transverse joints were dowel, you would start at one end of the runway and go down and walk it and go to the other end. The slabs step down about 1/8 to 1/4 of an inch from the adjacent slab. And we think, well, the unbound base probably led a little bit to that. And I did bring a piece of the airport with me. This is a piece out of that 26-inch diameter core.
Man, I wanted the whole thing.
Took that 35 years ago. It's still holding together. But this is the transverse joint, this way, the dowel bar. And the 36 is the upstream side, 37 is the downstream side. I'll leave this where you can kind of look at it. But you'll see the void beneath, and you'll see epoxy in there. So that void was there. It's on the top on the other side, which confirms what we saw in the X-ray that we showed you. And you can see that it was cast that way. It's not that the dowel worked in there, it was just cast that way. And so you're out there in the field, and one of the first things we thought about, well, they greased the dowels. Yeah, I put a lot of grease on that dowel. No! The grease will stay there and leave a void when the concrete gets placed. So all those little details, watch them carefully when you're out in the field. But you're welcome to take a look at this. It's, and this is the part, I think on this side is where the coffee cup was, down at the bottom. That had nothing to do with the problem. But you're free to take a look at that and all. I know I'm going way over time, but I'll stay as long as anybody wants to ask questions. But thank you.
So Puneet, you're gonna coordinate?
Yeah.
Just like have a short discussion with the students for a little bit?
Oh, yes, yeah.
Okay.
Yeah, what?
So Puneet is gonna...
Hey. Oh, well, thank you. Enjoyed it. Thanks for coming. I appreciate that.
Thank you so much for a wonderful.
Oh, you're welcome. Thank you. Appreciate it.
So we are like student chapter of ASC TNDI.
Yes.
So we take this opportunity to know more about, learn more from our
Yeah.
guest speakers.
Okay.
So this is the opportunity we have time until 3:30, and we can, if
No, yeah, I'm here till, I've
have
got an
questions?
appointment at 4:30. Other than
Yeah.
that, I'm free.
Awesome. It's excellent.
Well, I hope it was okay. You can see I get wound up a little bit.
I really like it. I have an idea.
Yes.
So this is a case study.
Yeah.
Any documentation about that?
It's on the website, under the, it's written up on the online part, because it's been pushed on online.
Is it from your company or from the
we-
management?
Oh, you mean this case study?
This case study.
Oh, well, actually, this is two talks that I pulled together.
Uh-huh.
One, the first part on the payment management was a paper I gave to
Way and B is just.
That's what I'm
and
asking is, that was a really good thing that I did as a project for the students.
Oh.
And I think we have maintenance and rehabilitation type of classes.
yeah.
So a lot of case studies from asphalt pavement, but I don't have.
I could send you the paper
They're out there all the time,
from Quebec.
you know, trying to keep.
I'm trying to think, and the repair stuff was,
Was it the 8R that you mentioned that you have the surface cracks? Was that the 8R?
8 right, yes, the 40-day one,
Yeah,
8 right. Let me look and see, I've got so much stuff, where is it? But I can send you some stuff that maybe you can turn
Present
into.
it, some kind of a project.
Yeah,
Well, they, you know, they.
Things that just talked about it,
yeah,
but not the solution.
yeah.
And,
Well, and that's what I do in 498, like the one with the big core. That's one of the cases that I cover in there, where we go through and talk a little bit about what's the problem. And then you try to get students in class or online to discuss, well, what do they do, what would they do? And then you get into, well, here's the investigative data, now what would you do? And come to an answer. But let me see what I can find
I'll follow up with you then, yeah?
on 8 right when I get back home and look
Okay,
at my
yeah,
hard
let's
drive.
follow up, we'll keep in touch.
A lot of things, and
But I mean,
Okay.
this was really great, I liked it. Did you guys enjoy? Huh?
Oh, yeah.
Huh?
I hope you did.
Yes.
As I always tell people, I always look to see if people throw rocks or tomatoes. And if they don't throw rocks or tomatoes, then I say, it must have been okay.
Yeah, there's one thing that I'm afraid now, because back to back to concrete, so now, you know, what's going on here?
Well, I could bring you I can bring you some on asphalt. The shear layer is an interesting one.
Which problem was this?
This is a quote from the
35-year-old.
airport, 35 years old.
Well, that core is 35 years old. That concrete is
44, 45?
What did you cover this with?
it's 40 years old. But it's been out of the slab since 1987.
Is this the temperature reinforcement?
Yeah, no, that's the cage for the dowel bars
Okay.
that holds the dowel bars in place. And I just cut it down, one, to something I could handle, but also to show the void on the top of the dowel on one side and the void in the other. If you remember the pictures, those transverse joints were set down like that.
Mm-hmm.
There's 1¼ dowels on 12-inch centers across that joint. How did those slabs do that with 1¼ dowel bars in there? The only way they can do it is if there's voids around them, because you're not going to break the dowel bars. We didn't break off the concrete. Concrete does weird things when you look at it. So, but
Thank you very
Thank
much.
you so much again. I have to now leave for the campus.
understand.
Appreciate it. Yeah.
Good.
And looks like you have your right. If you need anything.
Oh yeah, and he said they wanted to meet.
Yes.
Yeah.
We'll have a meet and greet session.
Yeah.
Yeah.
Well, thanks again.
Good.
Charlie.
Hey,
Take care.
appreciate
We'll
it.
keep in touch,
We'll
yeah.
see you. Take her easy.
We'll
All right.
see
Thank you very
Good
much.
time.
Yeah.
And don't forget, sign up for CE 498 this summer.
Sure. Okay. You wanna sit and
Sure.
start?
I'll just grab a seat here and put this in here. So yeah.
I can check. You guys can check.
I've got my
Get your flash drive, right?
yeah. See what I got here.
Okay.
Got too much stuff in my pocket. Yeah, and you're welcome to keep that
No, yeah,
presentation.
we have to.
No,
we
that's,
usually keep it here. We'll be here.
yeah, you
Yeah.
keep that if you want, that's not a problem.
Yeah.
Okay, good. Okay,
Hey.
y'all wanted to chat or?
Yeah.
This is Chuck French, he's my driver for
Alright.
today. But Chuck is an aeronautical engineering graduate from U of I, 1967.
Wow.
So he understands what's going on too. He's